Note, with no further ado, I'm going to pass it over to Michael.
So, thanks, and appreciate being here and talking about our new system. We're going to put some pellets in it next week and start testing it. But we actually have a lot of different systems on campus, because one of the goals that we have is not just to optimize cost per CO2 or something, but we want to have technology that our students get to see, that they get to interact with, that there's data from, they can see how things work, analyze how things work, how they don't work. And so we have existing PV, we have wind on a remote, one of our remote classrooms at an experiment station in Tully. We make biodiesel, and we have a fuel cell. And a lot of these projects, NYSERD has been very helpful in helping us get this started. This is actually a view of our new Gateway building from the guard shack as you enter the ESF campus. And it's a location that until we built this building, you probably wouldn't know you were entering the ESF campus, because you're sort of looking at the back of a couple buildings, the carrier domes beside you, and a lot of people didn't know we were something different. We've sort of made an impression with this building, have a different structure, a different look, to let people know we're here. We've built a lot of features into this to make it what we think will be a high-end LEED Platinum building. We have rain gardens, a fairly extensive green roof, which will use a natural plant community, sort of very innovative. Our energy use in the building is going to be very low. We're going to put some PV on another part of the roof. We've got a solar thermal demonstration as part of it, as well as a CHP system. This has our admissions office, our community outreach, and our conference facilities, and a place for people to eat. So it's also dramatically different compared to where most people put their power plants. Right? So most people take their power plants, they shove them out the back, they never want anybody to see it, it's dirty, it's messy. We're going to have ours in the front door, and when people come in, they're going to see a sign that welcomes them to come down to the viewing window and see this facility, because we want people to interact with energy. We want them thinking about energy and thinking about sustainability. And so the building's designed as a teaching tool. We started with the building before we built the system, and a typical building, if we had built it to code, would have used about 120,000 BTUs per square foot per year. We're going to be at just over 40,000, so we have about a 64% reduction in our energy use compared to code. So we've done a lot to try and make this building energy efficient, to reduce how much energy we need, because we think actually that's the cheapest way to produce energy is not to use it. Right? So that's a savings even before we get there. We did a lot to minimize the energy use, and one of the interesting features I particularly like, when you look at this side of the building, this is a westerly wall, and if we put a lot of glass there, we would have had a lot of heat gain. We would have needed very high technology windows like in this building. Neil didn't have the money for those windows, so we had to do something a little different. So we put in these, the architects designed these, they call them flipper walls, even though they don't move. So the windows actually face south, and there's an overhang and shading. So we get natural light that we have, we can minimize the artificial light, but we really minimize the solar gain we get from that westerly sun. So we have a dramatic reduction in air conditioning needs in the building. And we use a lot of natural ventilation. And when we hired these architects, they said, you know, if you build a building right in Syracuse, New York, you need air conditioning about 5 days a year. And we may be a little more than that, but it won't be dramatically more. You really minimized how much air conditioning we would need. So our goals that we had, President Murphy made a commitment, part of the President's climate commitment, to be carbon neutral as a campus by 2015. That is something we're aggressively pursuing. We also are mindful that it's not just our place in the world, but how we contribute to emissions and emission reductions right around Syracuse, so local emissions are concerned. We want to improve how we use energy, so how efficient we are at converting primary energy into something that's a good energy service, like heat and things like that. We want to reduce our fossil fuel use and provide a positive return on energy invested. Even though I'm an economist, I've got plenty of colleagues at ESF that are ecologists and other things, and so they think economics are missing something, and so they focus a lot on teaching what's the energy return on the energy investment. Does that give us a positive return? So we focus on that. We teach our students about it, and we wanted to see that we had a positive energy return in what we're doing. Because we're not, rolling in dough from the state of New York, we want to have a positive net present value of this investment. We want to have, and we also look, and even though right now natural gas is pretty cheap and it looks like there's a lot of it, we see future volatility of prices, and we wanted to reduce our exposure to that. We also wanted something that's a teaching tool. So we could have optimized the system and put in just one technology and done one thing and potentially saved a little bit more energy or a little bit more emissions. But we wanted some things, so we had different technologies that we could compare and contrast. So we have an educational goal that went alongside what we were doing. So the technology, we looked at several different things. We adopted a set of microturbines that I'll show you the system in a minute. A wood pellet boiler that produces high pressure steam, and then a back pressure steam turbine to turn that into electricity, and some low pressure steam for heating some buildings. We looked at a pure gasifier that would run a genset. Weren't quite sure that was reliable enough at this scale to work for us and be a reliable system. We wanted biomass to be part of the solution. We believe it's a cost-effective, renewable energy that New York has a lot of. We ship a lot of dollars to buy fuel from outside of the state, and we like investing some of our dollars in the New York economy and local production of a local fuel. We chose pellets over wood chips, in part because of our urban environment. It's cleaner, it's more dense, fewer deliveries, neater way to keep it. It's more automated, so we less issues with equipment jamming and things. And then because actually the moisture's already been taken out, it's more efficient burning at our site. So a lot of times when people look at the price of chips and the price of pellets, they forget that the chips have a bunch of moisture, and you've got to use some energy to drive that moisture off. You've already paid for that in the pellets. System size, as Hugh said, we focused on how much thermal do we need, and we really looked at 3 sizes of systems. One would have done the entire campus. One is the gateway building, the medium system, plus the 4 closest buildings. There's 4 buildings that are basically just adjacent to it, and then a small system that would have been just the gateway system. So we adopted this medium system really because we didn't want to run longer steam lines. We didn't find it cost effective to the additional 4 buildings we have on campus. And this takes care of about 60% of our thermal needs, 65% of our thermal needs with this system. So we felt that was the right system. We also looked at a variety of sizes of absorption chillers, but we actually had existing electrical chillers that are pretty efficient. The absorption chillers couldn't match that efficiency. We were generating so much heat with the biomass system that we actually found it economic to shut it off in the summer and just draw the cool water from a building next door, a chiller that already existed. We didn't even have to buy one for this building because the cooling needs are so small, rather than adopting an absorption chiller. The microturbines that I mentioned, we run year-round. So the components of the system are set up like this. This is that front corner of the building. So we deliver pellets to a bunker silo type of arrangement in the back. That feeds a Chiptech gas fire close couple boiler. From that we produce 125 to 130 psi steam. That steam is fed to a Carrier micro steam turbine. So that's a unit that is pretty small scale, produces around 200 kW in our configuration. As the steam moves through, generates some electricity, lowers the steam to about 15 to 20 psi. That's what we need for the heat in our 4 existing buildings. So that's where we're using that. We size the boiler to sort of run base load during the 8 to 9 months that it'll run. And we put in a similar sized natural gas boiler. We actually have a summer boiler in case we need it. We use the natural gas technology to follow loads. So the wood system, to run efficiently, likes to run at a constant load. If you start cycling it, you lose efficiency fairly quickly. But by running that at sort of a steady base load sense, we can cycle with the natural gas units to meet all of our peak thermal needs. Then we have 3 capstone micro turbines. They're part of a Reliaflex system. So those 3 produce electricity, waste heat. The waste heat goes to a heat recovery boiler, which generates some low pressure steam. So during the cold months when we're needing lots of heat, we have the biomass system supplemented by the natural gas, producing heat through the micro steam turbines, supplemented by the heat from the capstones through the heat recovery boiler. In the summertime, we're getting all the heat we need for the 4 buildings plus Gateway from just the micro turbines. So we shut off the wood boiler in the summertime. The blue units, even though I didn't label them, are the air handling units for the building.
Mike, yep, the micro turbines are running on gas and stuff.
They're on natural gas. Yeah, the technology that we chose, the Chiptech technology, is sort of what they call a close couple gasifier. So it gasifies, but then the gas is not treated, it's not cooled, it's burned immediately in a boiler. So it would need to have additional equipment to process it, to use it for other technology. And right now, Capstone doesn't feel their equipment will run on biomass, gas from a biogas from wood. It has enough heat content in landfill gases, but not in what's produced by biomass for them. So I think they're still working on developing that, but right now they didn't have a technology that did that. On the energy side, and for those of you that are metric, you can just substitute MMBTU for gigajoules, and you're close enough. But basically 50,000 million BTUs of energy is what we need. And so I put the delivered energy on both sides here. The existing conversion efficiency of our purchased steam and electricity was 52%. So about 48% of the energy that went into those systems is wasted. So we had 95,000 million BTUs of primary energy going in. 45,000 is wasted, 50,000 delivered as useful heat and power to the campus. With the Gateway system, we're basically cutting our losses in half. We get about 76% efficiency. So we've eliminated 30,000 million BTUs or 30,000 gigajoules of losses, basically fossil fuels. And we've also substituted now about 55% of our input fuels are biomass. So about 35,000 of the 65,000 is biomass. So 65,000 gigajoules of fossil energy is saved with the system, fairly dramatic. You know, a little more than half of that's by fuel switching, and the other half is by efficiency. And so the final thing, you can see more about this and other things. And I have a new colleague who's our sustainability coordinator, a grad student, and she's actively recruiting friends on Facebook. So it doesn't mean much to me, but it does to her.
And so I guess we can ask a question. I didn't mention this, but if you have any questions for Mike, we could take those now. Did you, as a
Mike, you mentioned that one of your objectives is to achieve a positive net present value.
Yes.
Does this include subsidies, or this is based on the actual possibility?
It's both. With the system cost about $3.2 million, and we are going to save about $400,000 in the first full year of operations. So it actually, over a 15-year time frame, has a positive $1.5 million NPV, including a $1 million subsidy. If we take that away, it's a $500,000 positive NPV. So we actually have a positive return with and without subsidies. So we think it's a good investment either way.
What's the delivery schedule look like for the few of the items?
We actually, we thought we were going to have roughly 18-ton deliveries every other day during the peak season. We went out to bid, and we've just selected a delivery a supplier and delivery service. They actually have a 30-ton truck, and so we'll see deliveries probably 2 to 3 per week with a bigger truck. So it's really not too bad. They will deliver and be gone from campus before 8 in the morning, and that's probably 2 hours before most of our professors or students show up. So yeah, seriously, we did talk to them and made sure timing would be such that it isn't a huge thing, but they will be backed in, and we'll could tie up a little bit of traffic if it was right in the middle of the day.
So how roughly
And
long will it take to download?
It's about 45 minutes, and we have about 5 to 7 days worth of storage, depending on time of year. So if there's bad weather and they have to miss a few days, we can carry through for the time frame.
Can you comment on the geographic region that is providing the source of the biomass, and also the length of the contract?
Yep, it's 3-year contract with a possible extension. Really, I think the only interest was from New York pellet providers. The delivery service is actually Sandry, which they bought New England Wood Pellets delivery business, and so they actually own the trucks. They're a Massachusetts company, but the source will be either the New England Wood Pellet plant in Schuyler, New York, and they also have one in Deposit, New York. So that's.
So in the calculation of the net present value, you make an assumption about the cost of the fuel over the 15-year period?
Yeah, we did, and basically we had equated the escalation rate of the wood pellets and electricity and natural gas at about the same rate. We actually think the other fuels will probably grow faster than the wood pellets, but we viewed them as growing at about the same. So we started off at where they were relative to each other today, and we just see them growing fairly similar.
So the assumption is that the wood pellets will be transported by truck?
Yes, yeah, there's a truck delivery, either auger or pneumatic delivery. And one other thing we're working on, we actually are growing shrub willow as an energy crop, and we're trying to work with another local provider who could source some pellets made from our willow, and I think we've just found one that will be able to help us with that. It's getting it at a small scale has been difficult, but we'd like to self-supply with some of our willow as a source of pellets as well.
The adjacent 4 buildings, those currently run on steam?
Yeah, they run on steam that we've been purchasing from SU, and SU will actually still provide half of one of those buildings, high-pressure steam. So, and our existing the remaining buildings are still provided with steam we purchased from SU.
So you calculated an optimum size, a median size to provide those 4 buildings, a certain amount of pipe run to get steam in, and beyond that, there was so much heat loss that it wasn't worth going further?
Well, part of it was sort of it wasn't so much the heat loss, it was the cost of running that steam line. There's a little bit of heat loss. It's the complication of that system. We literally just had to run from this building across a 2-lane road, and we were into each of the other 2 buildings. So it was a relatively simple system for us. If we had run to the other buildings, the distances were further, and it would be a more complicated system. We're actually looking at whether we can add another CHP to serve those other buildings in a sort of a second